Tonight, we're going to explore one of the most extreme cosmic phenomena ever uncovered by human ingenuity. Imagine a world where every 111 Earth days, it is violently dragged toward its parent star, closing to just 1/30th the distance from the Earth to our Sun. Within mere hours, this crushing proximity causes its global temperature to skyrocket by over 200 degrees Fahrenheit, more than 120 degrees Celsius, before it is flung back out into the freezing dark to await the next roasting. Welcome to HD 80606b. To put that scale into perspective, consider our own home. Here, a mere global temperature rise of 2 degrees Fahrenheit, about 1.2 degrees Celsius, is already enough to unleash wildly erratic climate disruptions. Tragically, European nations recorded over 10,000 excess deaths during the record-breaking heat wave that engulfed the Western continent late last June. Stay with us, and by the end of tonight, tracing the latest discoveries from the James Webb telescope, you will understand exactly why this planet is forced to undergo such brutal extremes. Before we dive in, if you share our passion for drifting through the cosmos, please take a moment to like this video or subscribe. It's a small gesture, but it goes a long way in helping this channel connect with more inquisitive souls like yourself. Now, let the journey unfold. For many generations, our finest minds looked up at the starry night sky and believed they had figured out the grand architecture of the cosmos. They crafted a beautiful, orderly blueprint, a classical doctrine of how a solar system comes to be. It was a theory that mirrored the steady, predictable rhythms of an old grandfather clock, comforting in its structure, reassuring in its logic. It told a comforting story of a universe that was safe, predictable, and deeply anchored in common sense, where order ruled the vast, velvet emptiness. At the heart of this traditional understanding lies a concept known to astronomers as core accretion, which we can simply think of as the slow, gravitational snowball effect of the cosmos. Imagine a vast, swirling disk of dust and gas surrounding a newborn star, an ancient nursery left over from the collapse of a stellar nebula. In the quiet darkness of this disk, tiny grains of cosmic dust began to gently bump into one another, sticking together through static electricity, much like the soft gathering of dust bunnies under an old, familiar workbench. Over millions of years, these small clumps grew into rocks, then boulders, and eventually into massive planetary seeds. The classical theory dictated that a planet must first build a solid, rocky foundation, a heavy core made of iron and stone, before it could ever dream of becoming a gas giant. Once this rocky heart grew heavy enough, reaching a critical mass of roughly 10 to 15 times the weight of our own Earth, its gravitational pull became an irresistible vacuum cleaner, suddenly and violently snapping up the surrounding blankets of hydrogen and helium gas to drape itself in a massive, thick atmosphere. But this cosmic construction required a very specific workshop, a quiet zone far removed from the blistering fury of the young parent star. This brought about the fundamental concept of the snow line, the invisible frost boundary in space. The cosmic shoreline where the heat of the star finally fades enough for volatile gases to freeze solid. Inside this boundary, close to the star's roaring hearth, it was simply too hot for anything but metal and rock to survive in solid form. Any ice or gas would be instantly vaporized, blasted away into the void by the fierce solar winds. However, once you stepped across that quiet, frozen threshold of the snowline, the universe changed completely. Out there in the deep freeze, water, ammonia, and methane did not drift as invisible vapor. They froze into solid ice crystals, acting like cosmic snow and primordial pebbles. This icy gravel provided an abundance of solid material, a rich quarry from which a young planet could rapidly assemble its heavy core. It was out there, in the lonely, cold expanses, where the sun's warmth was nothing more than a distant, twinkling memory that the true heavyweights of our solar system could be forged. Because of this, the old rules of astronomy were unyielding gas giants, like our own familiar Jupiter and Saturn, belonged exclusively to the outer darkness. It was an absolute law of nature, carved into the very physics of planet formation. A giant planet required the freezing dark of the outer porch to gather its ice and hold on to its massive, bloated belly of gas. The inner sanctuary of the solar system was reserved solely for the small, hardy worlds of rock and iron, like Mars, Venus, and our own gentle Earth. This was the elegant harmony we believed in, a place for everything, and everything in its place. It was a universe that made sense to us, a well-managed estate where the giants stayed in the backyard and the rocky worlds tended to the front garden. We slept soundly, knowing the cosmos followed this clean, predictable script. Little did we know, deep in the velvet expanse of the cosmos, a rebellious world was waiting to shatter the old rulebook entirely, challenging everything we thought we knew about the night sky. For a long time, we rested easy in our traditional understanding of the night sky, believing that nature followed a strict, orderly, and comforting blueprint. But in the quiet autumn of 1995, that comfortable certainty was shattered forever. It was a moment that sent a profound tremor through the scientific community, an intellectual earthquake that began in a peaceful observatory nestled in the hills of southern France. Two Swiss astronomers, Michel Mayor and Didier Queloz, were peering into the velvet darkness, tracing the subtle, almost imperceptible wobbles of a distant sun. What they stumbled upon did not just add a new name to the celestial charts. It fundamentally broke the established laws of cosmic architecture. It was the discovery of a world known as 51 Pegasi b, and with its birth into human knowledge, the universe suddenly became a far more strange, wild, and unpredictable place than we had ever dared to dream. The star itself, 51 Pegasi, is a steady yellow beacon sitting roughly 50 light-years away from our backyard porch, a star remarkably similar to our own familiar sun. But the companion world they found hugging this star defied all common sense. According to the old rules of astronomy, a giant gas world should only exist in the freezing, lonely outer reaches of a solar system, far away from the solar wind. Yet 51 Pegasi b was a colossus, a bloated ball of gas roughly half the size of our own Jupiter. But instead of taking 12 long years to complete its journey around its sun, this planet was flying through space at a dizzying speed, completing its entire year in just over 4 Earth days. It was sitting so close to its solar furnace that the concept of seasons vanished entirely, replaced by a permanent, blistering glare. To truly grasp the paradox of this alien world, we must visualize its location. It was parked more than 7 times closer to its star than the rocky, scorched desert of Mercury is to our Sun. To the astronomers of the mid-90s, this was an absolute impossibility. It was a world of ice and gas that had somehow broken through the frost line and marched straight into the fire. The sheer heat from the star was enough to expand the planet's atmosphere, puffing it up like a giant hot air balloon. To describe this unprecedented class of planets, scientists had to invent a completely new phrase, a term that sounded like a contradiction. In terms, the hot Jupiter. We can think of a hot Jupiter as a giant sphere of gas placed permanently on the most intense charcoal grill in the cosmos, seared by solar radiation 24 hours a day, with no hope of ever escaping into the cool shade of the outer porch. This discovery did not just challenge the textbooks, it provoked a fierce, generational resistance among the old guard of science. For months, many veteran astronomers refused to believe the data, suspecting a glitch in the delicate machinery or a misinterpretation of the stellar light. They argued that perhaps the star itself was simply pulsing, breathing in and out, mimicking the gravitational pull of a planet. It was a natural defense mechanism for minds that had spent decades relying on the neat, orderly arrangement of our own solar system. They wanted a cosmos that made sense, a universe that felt as reliable as a well-crafted grandfather clock. But as more telescopes turned toward 51 Pegasi, the truth became undeniable. The giant was real, and it was sitting right in the furnace. The revelation of 51 Pegasi b forced humanity to accept a humbling truth. Our own orderly solar system might not be the standard template for the universe, but merely one quiet, fortunate exception. It opened our eyes to the idea of planetary migration, the realization that giant worlds can drift, march, and fall inward from their birthplace, reshaping entire solar systems in their wake. As we let our minds drift into the deep, velvet dark of the night, we can appreciate the beautiful mystery of it all. The cosmos is not a fixed, rigid museum, but a dynamic, unfolding theater. And it was this very earthquake, this initial shockwave of discovery, that paved the way for us to eventually find even more extreme worlds that defy imagination, waiting quietly in the deep silence for a giant golden eye to finally see them. Once the door to the hot Jupiters was cracked open, the cosmos began to reveal even more eccentric secrets. In the year 2001, an international team of stargazers turned their sights toward a quiet star in the constellation of Ursa Major, the Great Bear. There, they detected the ghost-like signature of a planet that would challenge the very limits of celestial mechanics. This world was named HD 80,606b. It was not found by direct sight, for it was buried deep within the blinding glare of its sun, but rather through a delicate technique known as radial velocity. We can think of radial velocity as listening to the subtle heartbeat of a star, measuring the tiny rhythmic tug-of-war between the sun and its hidden companion. To understand this method, imagine standing by an old railroad track in the quiet evening, listening to the whistle of an approaching steam train. As the train rushes toward you, the pitch of the whistle sounds high and sharp, but the moment it passes and retreats into the distance, the sound drops to a low, hollow moan. This is the Doppler effect, a shifting of waves. In the vastness of space, when a hidden planet pulls its parent star slightly toward our earthly telescopes, the starlight shifts toward the blue end of the spectrum. When the planet loops around and pulls the star away from us, the light stretches toward the red. For most worlds, this shift creates a smooth, gentle wave on a graph, like the steady breathing of a sleeping child. But for this newly discovered giant, the graph looked like a sheer, terrifying cliff. The star remained calm for over 100 days, and then, in a matter of mere hours, its velocity plummeted and spiked with violent intensity. It was the unmistakable signature of a world on a wild, cosmic roller coaster ride, racing silently toward its sun at breakneck speed before being flung back into the dark. For 8 long years, this eccentric giant remained an alluring mystery, a collection of numbers on a page. The astronomers knew its orbit was shaped like a flattened oval rather than a perfect circle, but they did not know its true physical size or what secrets its air might hold. To unlock those mysteries, they needed to witness a transit. A transit is a cosmic game of shadows, a rare alignment where a planet passes directly between its star and our eyes on Earth. Think of it like a tiny moth fluttering across the lens of a massive, distant lighthouse. For a brief window of time, the moth blocks a microscopic fraction of the lighthouse's beam, causing the light to dim ever so slightly. By measuring exactly how much the starlight drops, astronomers can calculate the precise waistline of the planet, revealing whether it is a dense ball of rock or a bloated sphere of gas. But catching this specific shadow was a monumental gamble. Most hot Jupiters sit so close to their suns that they cross their faces every 3 or 4 days, giving scientists plenty of chances to observe them. But this world had a long, sweeping journey that took 111 days to complete. More challenging still, because its orbit was so tilted and stretched. The window of opportunity for it to pass directly in front of its star lasted for only about 12 hours. If the sky was cloudy, or if a telescope suffered a mechanical hiccup during those precise 12 hours, the opportunity would vanish. And the scientists would have to wait nearly 4 months for another chance. It was a high-stakes celestial lottery. In the cold February of 2009, a grand, quiet mobilization occurred across our planet. A global network of observers ranging from elite teams operating multi-million-dollar mountaintop observatories to dedicated backyard astronomers with small telescopes in their gardens all pointed their mirrors toward the same patch of dark sky. They sat up through the midnight hours, watching the digital readouts, waiting for the light to dip. The gamble paid off beautifully. Space-based telescopes and ground stations alike captured the precise moment the planet stepped into the starlight. This collective effort confirmed that the planet was a true titan, a gas giant roughly the same diameter as Jupiter, but 4 times more massive. More importantly, it proved that its atmosphere was surviving a brutal, periodic roasting. It was a triumph of human patience and cooperation, a quiet victory achieved while the rest of the world slept, setting the stage for an even greater eye to one day look upon this hellish world. To truly understand the path of HD 80,606b, we must completely forget the neat, round circles of our own familiar solar system. Imagine a perfectly round dinner plate. That is how calmly Earth travels around our sun. Now, imagine taking a rubber band and stretching it across a long dining table until it is pulled nearly straight, forming a long, skinny, squashed oval. That is the extreme path of this planet. It is an orbit so flattened that it behaves less like a proper planet and more like a wild cosmic slingshot. For nearly its entire year, the giant crawls at a sluggish pace in the deep, freezing dark at the far end of this long loop. Moving so slowly, it seems almost asleep in the shadows, but as it rounds the far turn, the iron grip of the star's gravity takes hold. The planet begins to plummet inward, accelerating faster and faster, turning into a runaway train falling down a steep mountain. It plunges straight toward the solar fires, hurtling through space until it grazes the very surface of its sun. Passing 10 times closer than our own scorched Mercury ever dares to go in a matter of mere hours, it whips around the star in a terrifyingly sharp, hairpin turn, gets blasted by unimaginable heat, and is then flung right back out into the freezing dark, slowly losing steam until it comes to a near crawl once again. How did human beings, sitting in quiet rooms millions of miles away, ever map this invisible roller coaster? We did so by watching the host star itself. As the planet crawls in the outer dark, the star remains perfectly still. But during that brief, chaotic moment, when the planet whips around the sun at lightning speed, its massive weight pulls hard on the star, causing the sun to suddenly lurch and wobble. Astronomers call this radial velocity, which we can think of as listening to the shifting pitch of a cosmic train whistle as it rushes past. By reading these sudden, dramatic shifts in the starlight, followed by catching the planet's transit, the precise moment it casts a tiny shadow across the star's bright face, like a moth passing a porch light, humanity traced every curve of this extreme celestial racetrack. With the reality of this strange world firmly established, a deeper question lingers in the quiet of the night. What unseen hand could bend the path of such a giant into so wild a dance? The answer lies in the dark. Invisible currents of gravity. Let us now drift into the silent choreography of the cosmos, where hidden forces and tidal friction slowly sculpt the destiny of this lonely wanderer. Tonight, we travel to a familiar corner of the northern heavens, into the ancient constellation of Ursa Major, the Great Bear, a stellar pattern that many of us have looked upon since we were boys, tracing the outline of the Big Dipper on warm summer nights. But deep within this celestial bear, far beyond what the naked eye can see, lies a grand and terrifying stage. This is a place where two mighty suns are locked in an eternal embrace, creating a chaotic environment that would forever alter the fate of the lonely planet caught between them. This cosmic stage is a binary star system, which we can simply understand as a majestic cosmic waltz, a grand dance where two stars are bound together by gravity, spinning slowly around a common, invisible center of balance. In this particular neighborhood of space, the dancers are named HD 80,606 and HD 80,607. They are near twins to our own familiar sun, glowing with a steady yellow light. If you were to stand in the deep space between them, you would see two brilliant suns illuminating the darkness. Each one a massive furnace of nuclear fire. In a simpler universe, these twin stars would go about their business in peace, their light shining out into the void like a pair of quiet lighthouses. But the geometry of this system is far from simple. It is a masterpiece of complex gravitational architecture, a tiered structure that astronomers call a hierarchical system, which we can think of as a strict family tree of gravity, where the larger, heavier members dictate every single movement of the smaller ones below them. To understand the sheer scale of this grand stage, we must look at the immense distance that separates these two sister stars. They are parked roughly 1,000 astronomical units apart from one another. An astronomical unit is the standard yardstick of space, representing the distance from our own front porch here on Earth to the warm face of our Sun. To put that in perspective, 1,000 astronomical units is an expanse so vast that it is more than 30 times further than the lonely, unfrozen kingdom of Pluto sits from our own Sun. It is a distance that takes a beam of light, traveling at its blistering speed, more than 5 full days to cross. You might think that across such a deep, silent gulf of space, the two stars would leave each other alone, operating as independent kingdoms in the dark. But gravity is a patient and long-lived force. It does not care about the vastness of the void. It reaches out across the light days like a silent, invisible tether, tying the two suns together in a permanent, unbreakable bond. It is this very distance that creates what we might call a slow, long-distance relationship between the two stars, a relationship that is quiet, subtle, and yet utterly transformative for the planet HD 80606b, because the second star, HD 80607, sits so far away. Its gravitational pull does not instantly yank the planet out of its orbit or tear it to pieces. Instead, it exerts a tiny rhythmic drag, a faint pull that accumulates over vast stretches of time. Astronomers refer to this as gravitational perturbation, which we can simply think of as a gentle, persistent cosmic nudge. Imagine a heavy grandfather clock with a swinging pendulum. If you were to walk by every single hour and give that pendulum the tiniest, most microscopic tap with the tip of your finger, you wouldn't notice a change at first. But if you kept doing it for 100 years, that pendulum would eventually begin to swing in a wildly different arc. This is exactly what the distant sister star has been doing to our planet for billions of years. From its faraway perch, it acts as an invisible, silent puppeteer. Every time the planet travels around its home sun, the distant star gives it a tiny gravitational tug, because the orbit of the two stars is tilted at a severe angle compared to the planet's path. This persistent nudging does something extraordinary. It slowly begins to destabilize the planet's world, warping its neat, circular route into something monstrous. It is a slow-motion haunting of an orbit, a relentless pressure applied across the dark, empty space that steadily robs the planet of its stability. Here, in the velvet dark, we encounter a grand mathematical symphony, known to astronomers as the Kozai-Lidov mechanism. Do not let the heavy name disturb your rest. We can think of this simply as the ultimate celestial seesaw, a beautifully balanced, slow-motion game of give and take played out by the unseen hands of gravity over vast stretches of time. It is a law of nature that acts like a cosmic sculptor, silently changing the shape of a planet's path in the dark while the rest of the universe slumbers. To truly understand this invisible machinery, we must first look at a fundamental rule of physics called the conservation of angular momentum. In the grand vocabulary of science, this sounds rigid and complex, but it is a concept we know intimately from everyday life. Think of a heavy, cast-iron flywheel spinning smoothly on an old, well-oiled steam tractor, or a classic wooden spinning top dancing on a hardwood floor. Once that heavy wheel gets moving, it possesses a stubborn desire to keep spinning, resisting any attempt to slow it down or change its direction. In the frictionless vacuum of space, a planet traveling around its star possesses this same stubborn, beautiful momentum. It is a divine bank account of motion that can never be overdrawn. The universe demands that the total amount of this spinning energy must remain perfectly constant. However, when a planet is trapped in a binary system with a distant sister star, a very peculiar loophole in this law is exposed. The universe allows the planet to alter its path, but only if it follows a strict rule of cosmic compensation. This rule governs the perpendicular component of angular momentum, which is merely a scientist's way of describing the invisible vertical spine of a planet's orbit, the unyielding axle around which the world revolves. The Kozai-Lidov mechanism dictates that while this vertical spine must remain perfectly locked in place, the orbit itself can tilt and warp, trading one characteristic for another in a permanent cosmic balancing act. This brings us to the great seesaw match between two primary features of any orbit: inclination and eccentricity. Inclination is simply the tilt of the planet's orbit, much like leaning a vinyl record at an angle on a flat tabletop. Eccentricity, on the other hand, is the measure of how squashed or stretched a circle becomes, turning a round hoop into a long, skinny oval. The Kozai-Lidov mechanism forces these two traits into an eternal game of cat and mouse. When the planet's inclination drops, meaning its orbit flattens out to match the tabletop, the eccentricity is forced to skyrocket. The round, safe orbit is ruthlessly squashed, stretched out like a piece of warm taffy until it becomes a razor-thin, elongated oval. This celestial exchange is not a sudden catastrophe, it is a majestic rhythmic cycle that takes millions of years to complete a single breath. For countless generations, the planet HD 80,606b found itself trapped in this very cycle, but this cosmic seesaw cannot be triggered just anywhere. It requires a very specific, dramatic catalyst. Astronomers have calculated that this mechanism will only spring to life if the initial tilt of the planet's path crosses a critical threshold of 39 2/10 degrees relative to the distant star's orbit. If the tilt is a fraction less, the system remains stable. But in the case of our lonely gas giant, the initial tilt was a staggering, near-vertical angle of 85 degrees. It was a perfect, dangerous alignment, a cosmic trap waiting to be sprung. With the tilt sitting so high above the critical threshold, the distant sister star began its patient, relentless work. Over the course of eons, the gravity of the faraway sun began to push the planet's orbit down, flattening its tilt, and as the inclination fell, the universe demanded its payment. The orbit of HD 80,606b began to deform, stretching out farther and farther into the darkness. The circular haven where the planet was born was slowly obliterated, reshaped into the hyper-eccentric, comet-like racetrack we observe today. The Kozai mechanism has done its ancient work, squashing and stretching the orbit of our lonely giant, HD 80,606b, into a razor-thin oval. Now, we witness the terrifyingly beautiful moment when this world pays the price for its eccentric lifestyle. As the planet plunges toward its closest approach to the star, a silent, invisible force rises up to greet it, a phenomenon known to science as tidal friction. We can think of this simply as a majestic gravitational braking system, an almighty anchor thrown into the fabric of space-time itself, converting raw cosmic speed into pure, suffocating heat. To understand the immense power of this moment, we must picture the planet at its point of closest approach, just 0.03 of an astronomical unit away from the roaring face of its sun. At this incredibly short distance, the star's gravity ceases to be a gentle guide and becomes a monstrous, crushing hand. This triggers the law of gravitational tidal forces, which is merely a scientist's way of describing the violent difference in pull felt across the body of a single world. Because the planet is so massive, the side facing the star is gripped by a significantly stronger gravitational pull than the side facing away in the dark. Imagine holding a soft lump of bread dough or an old, pliable rubber ball and pulling hard on one side while holding the other side still. The ball deforms, losing its perfect roundness. This is exactly what happens to our gas giant. The star's immense gravity stretches and warps the planet, pulling its round, majestic sphere into a bloated, elongated egg shape. But the planet is not sitting still. It is rotating on its axis, spinning through this intense gravitational vice. As it turns, the bulges of gas are continuously forced to shift across the planet's body, creating a relentless mechanical churning deep within its interior. Astronomers call this process tidal heating, which we can understand through a simple, earthly analogy. Think of taking a thick, heavy piece of copper wire or a lump of cold modeling clay and kneading it repeatedly between your palms, bending it back and forth with steady force. In a matter of moments, you will feel the material grow warm, then hot to the touch, as the internal friction of the molecules creates thermal energy. On a grand, planetary scale, this is exactly how the star tortures the giant. The relentless squeezing and flexing acts like a cosmic handsaw, generating an unimaginable amount of friction at the atomic level. This cooks the planet from the inside out, heating its deep, rocky core independently of the blistering starlight, scorching its external face. This internal friction does something even more profound. It acts as a massive, invisible brake on the planet's motion. This is the true essence of tidal friction. Imagine a heavy train locomotive, a roaring iron beast, descending a steep mountain pass to control its terrifying speed. The engineer applies the heavy iron brake shoes against the spinning steel wheels. The screaming friction slows the train down, but it also releases a shower of sparks and immense heat, converting the train's kinetic energy into thermal energy in the frictionless vacuum of space, where there are no air molecules to slow a planet down. Tidal friction serves as those heavy iron brake shoes. Every single time HD 80606b whips around its star in that sharp, hairpin turn, the internal friction steals a massive fraction of its speed, turning its motion into heat. The consequences of this gravitational braking are written into the very future of the planet's orbit, because the planet loses a small amount of its kinetic energy during each close shave. It leaves the star's presence with less steam than it had when it arrived. It no longer has the energy to climb all the way back out to its original, distant resting place in the icy outer dark. Every 111 days, the long stretched rubber band of its orbit is subtly, imperceptibly shortened. The far end of the loop is being reined in, pulled closer and closer to the stellar furnace with every passing lap. This slow-motion collapse of an orbit is a process known as tidal circularization, the inevitable rounding out of a wild trajectory. As these invisible forces patiently tame the wild giant, out in the deep silence, we turn our eyes to the tools we built to watch it unfold. For years, we could only capture a blurry whisper of this distant furnace, but a quiet revolution was coming, a majestic passing of the torch from the pioneering eyes of Spitzer to the golden, unmatched vision of the James Webb Space Telescope. For generations, humanity looked up at the night sky using only our natural sight, limited entirely to the narrow band of visible light that passes cleanly through our atmosphere. But the universe holds its most profound, mysterious secrets in a spectrum that remains completely invisible to the naked eye, the infrared realm, the silent world of pure heat. To see this hidden reality, we had to build telescopes that could leave the Earth behind, launching our instruments far beyond the distorting blankets of our atmosphere. Among the great pioneers of this golden age of discovery was the Spitzer Space Telescope, a faithful, quiet, robotic scout launched by NASA that served as our first true sentinel in the infrared dark, revealing the warm, glowing embers of the deep universe. In the quiet months of the year 2007, a brilliant astrophysicist named Greg Laughlin and his team of dedicated researchers decided to take a monumental gamble with this aging space telescope. Spitzer was approaching a critical turning point in its historic journey. It was running dangerously low on its precious supply of liquid helium, the ultra-cold coolant required to keep its hypersensitive instruments chilled to near absolute zero. As the telescope prepared to enter its final, warm mission phase, Laughlin decided to point its fading mirror directly at the constellation of the Great Bear, locking its gaze onto the mysterious path of HD 80,606b. They commanded the telescope to stare at this lone world for 30 consecutive hours, ridding the machine of all other tasks, waiting patiently for the giant planet to execute its terrifyingly fast, hairpin turn around its parent sun. It was a moment of pure scientific suspense, capturing data during a narrow window of time that would never come again. The technique Spitzer utilized during those breathless hours of observation is known to astronomers as broadband photometry. While the phrase sounds complex and highly specialized, we can simply think of this as a crude cosmic thermometer, an instrument designed to look through a wide, soft lens to measure the total, collective glow of infrared heat radiating from a distant object. It did not possess the delicate power required to separate the incoming starlight into fine, individual threads or detect the unique signatures of specific chemical elements. Instead, it operated much like an old-fashioned thermal imaging camera, or a gentle hand placed near the coals of a dying campfire, judging the intensity of the fire by the sheer volume of warmth radiating across the empty porch of space. It was an elegant but simple tool, a pioneering step that could tell our scientists how hot a world was getting, but could not yet whisper the secrets of what that world was actually made of. What Spitzer witnessed during that 30-hour vigil sent waves of astonishment through the entire scientific world as the gas giant made its desperate, accelerating plunge toward the stellar fire. Spitzer's instruments recorded a spike in infrared light, unlike anything humanity had ever recorded before. In a window of just 6 short hours, the temperature of the planet's upper atmosphere skyrocketed from a chilly baseline of 500 degrees Celsius, already hot enough to melt lead to a staggering, blinding 1,200 degrees Celsius. This was an instantaneous explosion of thermal energy, a global flash frying of an entire world. It was this very observation that earned the planet its immortal, poetic moniker in the halls of astronomy, the roasted exoplanet. For the first time in human history, we had not just found a distant planet, we had watched its weather change in real time. Witnessing a global season shift from a long winter to a hellish summer in less time than it takes a man to complete a single day's work. Yet, for all its magnificent success, Spitzer's historic discovery left the scientific community with a profound sense of longing. It had given us a tantalizing glimpse into the furnace, but it had left the portrait incomplete. Its wide thermal lens could only provide a blurry, aggregate measurement of the heat. It was as if we were standing outside a massive, roaring steel mill in the dead of night. We could see the bright red glow reflecting off the clouds, and we could feel the intense warmth radiating from the brick walls, but we could not see the actual machines moving inside. Nor could we tell what metals were being melted down in the crucible. Spitzer proved that HD 80606b was a world of absolute extremes, but it left the deep chemical identity of its atmosphere shrouded in the dark. It was a beautiful, necessary prologue, a magnificent passing of the torch to a new generation of technology that would one day pull back the curtain entirely, guiding us toward a deeper truth and guiding your mind toward a deep, undisturbed, and restful sleep. We have walked through the pioneering days of Spitzer, a faithful tool that gave us our first blurry glimpse into the alien fire. But science, much like the slow turning of the seasons, demands a grander perspective. To truly pull back the velvet curtain of the cosmos, we needed a marvel of engineering that would redefine our relationship with the stars. This gave rise to the James Webb Space Telescope, a $10 billion masterpiece of human ingenuity, a golden voyager launched into the absolute silence of the deep void to serve as the ultimate, unblinking sentinel of light, guiding our understanding of the deep night. To understand the true magnitude of this cosmic leap forward, we must look at the physical heart of this magnificent machine, its grand primary mirror. Think back to the pioneering Spitzer telescope, an elegant machine whose light-collecting mirror was a modest circle measuring a mere 0.85 meters across, which is roughly the size of a wooden wheel on an old farm wagon. Now, imagine the breathtaking scale of James Webb. Its primary mirror is a towering 6.5-meter monument of pristine engineering, composed of 18 individual hexagonal segments crafted from ultra-lightweight beryllium and coated in a layer of pure gold, so thin it would make a gold leaf on a fine antique frame look thick. This massive golden honeycomb acts like a grand funnel for ancient starlight, possessing an aperture which we can think of simply as the wide, light-gathering iris of a grand camera that is more than 60 times larger than the eye of Spitzer. It is a mirror polished to such absolute, terrifying perfection that if it was stretched to the size of the entire North American continent, the highest bump on its surface would be no taller than a single blade of backyard grass. This immense golden eye does not simply look at space. It is equipped with a suite of highly specialized instruments designed to perceive the invisible language of heat with unparalleled clarity. Chief among these technological wonders is an instrument known to scientists as MIRI, the Mid-Infrared Instrument. While the acronym sounds clinical and detached, we can understand MIRI as a masterfully crafted thermal camera, a device designed specifically to capture the longer, cooler wavelengths of light that radiate from warm gas and cosmic dust, because space is filled with freezing darkness. MIRI must be kept at an incredibly low operating temperature, cooled by a specialized mechanical cryocooler, which is merely an advanced vibration-free refrigerator, to just 7 degrees above absolute zero. This extreme chilling allows MIRI to see the deep universe without its own internal heat blinding the view. For the Planet HD 80606b. MIRI acts like a sublime and advanced night vision scope, capable of piercing through the thickest, most turbulent layers of alien smog to measure the deep, internal embers of the planet as it is roasted by its star. Working in perfect harmony alongside this thermal sentinel is another marvel of optical craftsmanship known as NIRSpec, the near-infrared spectrograph. In the grand vocabulary of astrophysics, a spectrograph sounds like a rigid industrial machine, but we can think of NIRSpec as an incredibly delicate cosmic prism, a masterful light splitter whose sole purpose is to untangle raw, messy starlight into its fine, individual component colors. NIRSpec is equipped with a revolutionary micro-shutter array, which we can visualize as a vast grid containing 250,000 microscopic window blinds, each one thinner than a human hair and capable of being opened or closed independently by a magnetic arm. This allows the telescope to isolate the light from hundreds of cosmic objects simultaneously, or, in the case of our lonely gas giant, to focus exclusively on the thin, fragile rim of light passing through the planet's upper atmosphere. When NIRSpec catches this filtered light, it performs the elegant art of spectroscopy, the scientific method of breaking down light to reveal the unique chemical fingerprints hidden within it. Just as a master locksmith can look at the fine ridges of a key and tell you exactly what door it opens, NIRSpec reads the missing dark lines in a spectrum to identify the precise atoms and molecules present in a world trillions of miles away. It transforms a blurry smudge of heat into a sharp, crystalline barcode of knowledge. Where Spitzer could only tell us that the furnace was hot, James Webb, through the combined magic of MIRI and NIRSpec, can read the exact ingredients being cooked inside the grand pot. We have marveled at the immense golden mirror of the James Webb Space Telescope and its chilled instruments waiting in the freezing void. Now, we unlock the true philosophical magic of its mission, to truly understand what happens when a giant world is shoved into a solar furnace. Human beings had to invent a completely new way of analyzing light. This revolutionary technique is known to astrophysicists as time-resolved spectroscopy. In the grand vocabulary of science, it sounds dense and intimidating, but we can think of this simply as a cosmic motion picture, a dynamic frame-by-frame film reel that captures the shifting fingerprints of chemistry as they transform in real time. To appreciate the immense leap forward this represents, consider how we used to look at the universe. For a long time, traditional spectroscopy was much like taking a single, static photograph with an old family camera. A scientist would look at a star or a planet, snap a picture of its light barcode, and get a beautiful, frozen snapshot of its chemical makeup at that exact moment. This worked perfectly for quiet, peaceful planets that stayed at a constant distance from their suns, where the weather never changed and the air remained perfectly still. But a single photograph is completely useless when you are dealing with a world as chaotic as HD 80606b. If you only take a picture before the planet plunges into the fire and another after it leaves, you miss the entire story. You miss the drama of the transformation. This is where time-resolved spectroscopy changes the rules of the game entirely. Instead of a single snapshot, the James Webb Telescope runs its light splitter continuously, second after second, minute after minute, hour after hour. It operates exactly like an old-fashioned reel-to-reel film projector from our youth, flashing dozens of individual images every minute to create the illusion of smooth, flowing motion. As the planet hurtles along its hyper-eccentric racetrack, the telescope records a continuous, unbroken stream of chemical barcodes. This allows our scientists to watch the atmosphere evolve dynamically. We are no longer just measuring a static state of matter. We are watching chemical reactions play out in real time on a planetary scale, witnessing an alien world breathe, sweat, and shift right before our eyes. To understand what the telescope is actually seeing during this cosmic motion picture, imagine a well-calibrated machine shop where a master craftsman is heating a piece of raw steel. As the metal absorbs the energy of the forge, its color changes from a cold, dull gray to a warm cherry red, and finally to a brilliant, glowing white. If you were to look at that metal through a specialized prism, you would see the very nature of its light waves shifting as the heat increases. On a cosmic scale, the James Webb Telescope is watching a similar grand transformation take place within the air of our gas giant. As the planet approaches its closest point to the star, the telescope focuses on the thin ring of starlight filtering through the planet's outer atmospheric shroud. This technique is called transmission spectroscopy, which we can understand simply as looking at a stained glass window while the morning sun shines brightly behind it. The different chemicals in the planet's air act like the colored glass, absorbing specific wavelengths of light and leaving dark, telling lines in the spectrum. Through time-resolved spectroscopy, scientists can watch these dark lines move, fade, and intensify as the temperature climbs by hundreds of degrees. The data rolling in from the telescope reveals a mesmerizing chemical shape-shifting event when the giant planet is resting in the cold outer darkness of its orbit. Its atmosphere is dominated by methane, a simple, cold-loving molecule made of carbon and hydrogen atoms that thrives in the peaceful shade. Methane leaves a very distinct, heavy signature in the infrared light, a thick barcode that tells scientists the world is at peace. But as the planet plunges into the terrifying glare of its cantin, or closest approach, the sheer kinetic energy of the rising heat acts like a microscopic wrecking ball. The intense thermal radiation slams into the methane molecules, violently tearing the hydrogen atoms away from their carbon anchors, breaking the chemical bonds entirely. In a matter of mere hours, as the old methane barcode dissolves into nothingness, a new chemical signature begins to emerge on the telescope's digital readouts. The loose carbon atoms, desperate to find a new partner in the scorching heat, grab onto the abundant oxygen atoms in the air, rapidly assembling into carbon monoxide. This is a molecule that loves the fire, thriving in conditions that would destroy lesser compounds. Through the continuous frame-by-frame view of time-resolved spectroscopy, Humanity is witnessing this molecular changing of the guard take place in real time. We are watching a global chemical conversion, an atmospheric rearrangement on a world 4 times more massive than Jupiter, compressed into a single afternoon. As we let our minds dwell on this magnificent capability, feel a deep, reassuring sense of comfort in the steady patience of human curiosity. We have built a machine capable of sitting 1,000,000 miles away in the silent dark, untangling the fast-moving secrets of a world trillions of miles further still. We are no longer blind to the dynamic rhythms of the deeper cosmos. The film reel of the universe is spinning smoothly, capturing every break in a molecular bond, every shift in an atomic alignment, with absolute, predictable precision. Let the heavy, comforting weight of this orderly knowledge settle over your eyelids now. The golden eye of Webb continues its quiet vigil, recording the great motion picture of the stars, while you are safe, protected, and free to let go of the waking world, drifting gently into a deep, undisturbed, and beautifully restful sleep. Armed with this revolutionary golden eye, the stage was finally set. Astronomers locked Webb's gaze onto the giant just as it began its desperate, accelerating plunge. Let us now drift into the quiet intensity of the control rooms for 24 breathless hours around the closest approach, a high-stakes vigil where decades of human theory finally met the unyielding, beautiful truth of raw cosmic data. Now, as we rest in this peaceful sanctuary, our thoughts travel across the vast, ink-black ocean of space, down to a quiet complex of buildings in Baltimore, Maryland. Here, within the softly lit rooms of the Space Telescope Science Institute, a dedicated band of men and women sat up through the midnight hours, their faces illuminated by the gentle blue glow of computer monitors. They were executing one of the most complex, high-stakes scheduling operations in the history of human exploration. This was NASA's Breathless Time Coordination Campaign, a masterclass in celestial logistics, where every single tick of the clock carried the weight of a $10 billion legacy. To appreciate the immense pressure resting on the shoulders of these engineers, we must first look at the unique, uncompromising nature of their target. The giant planet, HD 80,606b, does not follow a predictable, evenly spaced path that allows for casual viewing. It operates on a long, sweeping orbit that takes 111 days to complete, for nearly that entire time. The planet drifts in the lonely, cold shadows of the outer porch, far out of reach from any meaningful thermal observation. The only moment that matters, the absolute climax of its entire year, occurs during a vanishingly small window of time when the giant makes its terrifyingly fast hairpin turn around its sun. This critical moment is known to astronomers as Periastron, which we can understand simply as the solar hearth, the point of absolute closest approach where the planet grazes the very skirts of the stellar fire. If the scientists missed this brief, 24-hour window, their entire campaign would collapse into nothingness. They could not simply hit a pause button or ask the universe for a temporary delay if a single line of computer code failed, or if the telescope's massive mirrors drifted by even a microscopic fraction of a degree during those critical hours. The planet would whip around its star in the dark, unwatched, and the opportunity would vanish into the void. The team would be forced to wait nearly 4 months for the long loop to complete its course once again, wasting precious operational hours on a space telescope that is shared by thousands of astronomers across the entire globe. Every minute of James Webb's time is a rare, fiercely protected commodity, divided among the nations of the world like water in a desert. To claim a continuous, multi-hour block of this golden eye's attention was to hold a winning ticket in the ultimate celestial lottery. The coordination of this campaign required the team to consult a complex mathematical timetable known as the ephemeris, which we can think of as the ultimate cosmic roadmap, a highly precise ledger that calculates the exact position, speed, and trajectory of a heavenly body for years into the future. It is much like the worn leather-bound almanacs that old sea captains used to navigate by the stars, or the strict, ironclad timetables that governed the great steam locomotives of our youth. But unlike an earthly train, which might be delayed by a heavy autumn fog or a fallen branch on the tracks, a planet obeys the unyielding, clockwork geometry of absolute gravity. The engineers had to calculate the exact microsecond the planet would begin its sudden acceleration into the solar furnace, ensuring that the telescope was already in position, its instruments fully stabilized, and its golden eye wide open long before the fireworks began. This required the engineers to wrestle with a strict set of operational rules called pointing constraints, which we can understand simply as the physical safety limits of the telescope. The boundaries that dictate exactly how the machine can tilt without exposing its delicate heart to destruction, because the James Webb Telescope is designed to look at the cold, faint whispers of the deep universe. It must always keep its heavy, 5-layer sun shield turned squarely toward the blinding light of our own sun, the Earth, and the Moon. It acts like a man wearing a wide-brimmed safari hat on a blistering summer afternoon, careful never to tilt his head back so far that the sun strikes his eyes. The scheduling team had to orchestrate a complex, slow-motion pivot, aligning the giant telescope so that it could track the target planet as it flew past its home star, while ensuring that the freezing instruments behind the sun shield remained safely cloaked in a shadow that is colder than liquid nitrogen. As the final hours of the countdown melted away, the tension in the control room was palpable, yet entirely silent. The engineers uploaded a long, beautifully orchestrated string of commands, a digital script that would guide the telescope automatically, without any human intervention, across the deep gulf of 1,000,000 miles. Once those commands were sent, the team could do nothing but sit back, drink their black coffee, and trust in the absolute perfections of their math. They watched the telemetry data ripple across their screens, confirming that the telescope had locked onto the star system with absolute, unyielding precision. It was a triumph of human patience and meticulous planning, a moment where decades of theoretical physics and engineering prowess were compressed into a single, flawless day of observation. In this deep stillness, our minds can contemplate a beautiful dance of celestial shadows and light, a phenomenon known to astronomers as a secondary eclipse. While the name sounds clinical and detached, we can think of this simply as a cosmic game of hide-and-seek, a perfect line of sight where a giant planet completely vanishes behind the brilliant face of its mother star. It is an extraordinary geometric event that allows human beings, using the golden eye of the James Webb Telescope, to perform a miracle of measurement, isolating the pure, blistering heat of an alien world without ever seeing the planet itself. To truly appreciate the elegant geometry of this moment, we must first contrast it with the more common event we explored earlier, the primary transit. Think of a primary transit as a classic shadow play. Imagine sitting on a dark porch on a midsummer evening, watching a massive, glowing porch light. If a tiny fruit fly walks directly across the glass of the bulb, it casts a minute shadow toward your eyes, blocking a fraction of the light. That is a primary transit, the planet crossing in front of the star. But a secondary eclipse is the exact opposite. It occurs when the planet completes its loop around the stellar hearth and slides directly behind the star from our perspective here on Earth. To visualize this, imagine standing at the edge of a quiet harbor at twilight, looking out at a grand stone lighthouse. If a distant boat sails directly behind the massive stone tower, it is completely blocked from your vision. The light from the tower remains bright, but the boat has vanished into the blind spot created by the structure. In the vastness of space, when HD 80606b executes its secondary eclipse, it is swallowed up by the immense physical bulk of its sun, plunged into a temporary eclipse where its own light can no longer reach our instruments. Now, you might wonder why scientists would care so much about a moment when a planet disappears from view. The secret lies in the unique timing and the extreme nature of this planet's squashed orbit, because the planet accelerates to unimaginable speeds as it plunges toward its star. It reaches its point of closest approach right around the time this eclipse takes place. As the giant world sweeps around the side of the star, just before it ducks behind the stellar curtain, it turns its fully illuminated face directly toward our telescopes on Earth. It is experiencing its absolute midday, a global noon, where the atmosphere is being blasted by a solar furnace 10,000 times more intense than anything felt on Earth. The planet's day side is glowing white-hot in the infrared spectrum, radiating pure thermal energy like a freshly forged iron poker pulled straight from the embers of a blacksmith's fire. This brings us to the true engineering masterpiece of the mission, the light subtraction technique. This is an elegant mathematical and optical trick that allows astronomers to separate the heat of the planet from the blinding glare of the star. We must understand that even with the immense power of a $10 billion telescope, the star and the planet are located so far away, more than 200 light-years into the deep dark, that they appear to our eyes as a single, solitary pinpoint of light. They are blurred together by the immense distances of the void. James Webb cannot simply take a picture and see the planet sitting next to the star like a marble next to a basketball. To overcome this limitation, the telescope utilizes the geometric perfection of the secondary eclipse. First, as the planet hugs the side of the star just before vanishing, Webb measures the total combined light of the system. This measurement represents the light of the star plus the intense, glowing heat radiating from the planet's day side. Then, the geometry of the orbit takes over, and the planet steps behind the star. Suddenly, the planet's contribution to the light is completely chopped away, hidden behind the solar wall. Webb takes a second measurement, capturing the light of the star alone. By taking the first measurement and subtracting the second measurement from it, scientists perform a beautiful piece of cosmic accounting. The star's light cancels itself out, leaving behind the pure, isolated, and untainted infrared signal of the planet itself. It is a technique as clean and satisfying as a master woodworker shaving away the rough outer bark of a log to reveal the pristine, dark grain hidden underneath. It gives us a 100% pure look at the planet's thermal signature, completely free from the blinding interference of the stellar furnace. The golden eye of the James Webb Space Telescope had completed its 24-hour vigil at the point of closest approach, and the raw data had been beamed safely back across the dark gulf to Earth. When the international community of stargazers gathered in the summer of 2026 for the 248th meeting of the American Astronomical Society, the atmosphere in the lecture halls was electric. The digital readouts did not just reveal a minor variation in weather. They delivered a profound, jaw-dropping shock to the scientific world, revealing a thermal explosion so violent that it completely collapsed decades of cherished academic theories. The heart of this discovery lies in a staggering, unimaginable jump in temperature recorded by the telescope's infrared sensors, as the giant world, HD 80,606b, rounded the hairpin turn of its star. Its atmosphere experienced a sudden thermal spike of 1,100 degrees Fahrenheit, a terrifying surge that translates to a rise of 600 degrees Celsius. To fully grasp the sheer violence of this event, we must look closely at the precise data points. Before the planet began its final, desperate plunge into the solar fires, it was already sitting at a baseline temperature of roughly 900 degrees Fahrenheit or 500 degrees Celsius. This is already a hostile environment, hot enough to melt a block of solid lead on its surface. But within a narrow, breathless window of just 6 short hours, the temperature did not just creep upward, it exploded, soaring to a blistering peak of 200 degrees Fahrenheit above 2000, or 1,100 degrees Celsius. To visualize this extreme flash heating, think of an old, heavy cast-iron skillet sitting on a cool counter in a quiet kitchen. If you were to suddenly drop that heavy iron pan directly into the white-hot coals of a commercial blacksmith's forge, the metal would scream as it absorbed the raw energy, turning from a dull black to a glowing, translucent red in a matter of moments. On a global scale, this is exactly what James Webb witnessed. An entire planet, 4 times more massive than Jupiter, was flash-fried in the span of a single afternoon. This dramatic data point forced scientists to confront a fundamental principle of physics known as thermal inertia. In the elegant language of science, this sounds complex, but we know it intimately from our everyday lives. Think of a large, thick soapstone brick sitting beside an old stone fireplace. It takes hours of exposure to a roaring fire for that heavy brick to warm through. But once it absorbs that heat, it holds onto it stubbornly, remaining warm to the touch long after the logs have crumbled to cold ash. For decades, astronomers assumed that a massive gas giant planet with its thick, deep blanket of heavy Jovian gas would possess an immense amount of this planetary thermal inertia. They believed the thick air would act like a protective shield, absorbing the star's sudden energy slowly and smoothly, cushioning the deeper layers of the world from any sudden, violent shocks. This comforting assumption led to the creation of what scientists call one-dimensional radiative equilibrium models. These were the standard, traditional computer simulations used by generations of astrophysicists to predict the weather on distant worlds. We can think of these old models simply as flat, idealized mathematical blueprints, much like a neat, tidy spreadsheet or a simplified weather map in a morning newspaper. These simulations operated on the peaceful theory that a planet's atmosphere would always maintain a perfect, orderly balance between the energy it takes in from its star and the energy it radiates back out into the cold void of space. Like a well-calibrated home thermostat, keeping the parlor at a perfectly steady temperature. The models predicted that as HD 80,606b approached its sun, the temperature would rise along a smooth, gentle, and easily predictable curve. But the raw data from the 2026 assembly shattered these flat blueprints entirely. The real-world universe refused to follow the neat, tidy script written by human supercomputers. The temperature graph did not show a gentle slope. It revealed a vertical cliff, an instantaneous wall of thermal energy that the old simulations were completely blind to. The traditional models collapsed because they had treated the atmosphere as a static, quiet pond, failing to account for the terrifying reality of hydrodynamic shock waves. We can understand a hydrodynamic shock simply as an explosive, supersonic wave of moving gas, similar to the sudden, thunderous burst of white steam escaping from an overpressurized boiler pipe in an old railroad yard. When the day side of the giant planet was suddenly roasted by that intense solar radiation, the air did not sit still to absorb the heat slowly. Instead, the sudden, extreme difference in temperature between the blistering day side and the freezing night side created an immense pressure wall. This wall tore through the atmosphere at speeds exceeding 5 kilometers per second, completely rewriting the laws of planetary circulation. Furthermore, the old models had assumed the planet would remain cloaked in protective, reflective clouds of mineral dust. Instead, as the data proved, the intense heat triggered an instantaneous evaporation of those very clouds, stripping the planet of its armor and allowing the raw, unmitigated solar fire to penetrate deep into the lower atmosphere. As the echoes of that terrifying thermal shockwave ripple across the scientific world, we lift our eyes from the numbers to witness a deeper molecular transmutation. This sudden, crushing heat does not merely burn the air, it shatters the very foundations of chemistry. Let us now drift into the swirling cauldron of this hellish weather forecast, where ancient compounds dissolve and a violent chemical explosion reshapes the sky. Let us return our gaze to the upper atmosphere of that wild, far-off giant, HD 80,606b. Having witnessed the massive thermal shockwave that shattered the traditional computer models, we now observe a deeper, quieter transformation occurring at the molecular level. This is a spectacular chemical dance, a cosmic seesaw between two primary carbon-bearing gases, methane and carbon monoxide. It is a beautiful and fluid balancing act where the molecules themselves change their shape and allegiance, completely altering the identity of the sky in a matter of mere hours. To understand the rhythm of this molecular game, we must first look at the planet when it is resting in the quiet. Freezing dark at the far end of its 111-day orbit out there, millions of miles away from the blistering gaze of its star, the planet enjoys a long, deep winter. The atmosphere cools significantly, dropping to a baseline temperature where the laws of chemistry favor peace and stability. In this cold environment, the carbon atoms drifting through the air look for companions, and they find an abundant partner in hydrogen. Each single carbon atom tightly binds itself to 4 individual hydrogen atoms, assembling into a molecule we know intimately as methane. We can think of methane in this cold state as a sturdy, well-insulated structure, much like a heavy, tightly bound knot or a collection of small magnets snapped firmly together around a single iron core. For nearly 100 days of its year, the planet is completely wrapped in this thick, methane-rich shroud. When the James Webb Space Telescope first pointed its golden eye toward the planet during its approach, its spectrometers picked up a heavy, unmistakable barcode. The dark absorption lines of methane dominated the spectrum, revealing a world that was, for the moment, calm, dark, and chemically at peace. It was an atmospheric blanket perfectly suited for the deep freeze of the outer porch. But as the unyielding grip of gravity pulls the giant planet into its headlong, accelerating plunge toward the star, the environment changes with terrifying speed. Within a narrow window of just a few hours, the atmosphere is hit by that monumental surge of thermal energy, with temperatures skyrocketing by more than 1,100 degrees Fahrenheit, which is equal to a jump of 600 degrees Celsius. This sudden injection of raw heat acts like a microscopic hammer slamming into the atmospheric gases. In the world of physics, heat is simply motion, the frantic, violent vibration of atoms. As the temperature crosses a critical chemical threshold, the methane molecules begin to shake with uncontrollable violence. The delicate bonds holding the 4 hydrogen atoms to their central carbon anchor simply cannot withstand this mechanical stress. The kinetic energy of the star's radiation snaps the chemical ties, stripping the hydrogen atoms away and leaving them to drift aimlessly through the turbulent air like dry leaves caught in an autumn gale. In a matter of a single afternoon, the vast, global reservoir of methane is completely torn apart, dissolved into nothingness by the sheer brutality of the solar furnace. On the telescope's digital readouts back on Earth, scientists watched the heavy methane barcode rapidly fade, its dark lines vanishing from the spectrum like a morning mist burning off a quiet valley stream. Yet, in the grand economy of the universe, matter is never truly destroyed. It is merely rearranged. The carbon atoms, now completely naked and isolated in the blistering heat, find themselves surrounded by a new, highly reactive environment. They are desperate to find a stable partner that can survive the intense radiation of the solar hearth. They turn away from the flighty, lightweight hydrogen atoms and lock onto the heavy oxygen atoms floating within the atmospheric mixture. A single carbon atom snaps together with a single oxygen atom, creating a dense, incredibly resilient compound known as carbon monoxide. We can think of carbon monoxide as the heat-treated steel of the molecular world. Its chemical bond is one of the strongest known to science, an ironclad connection that thrives in temperatures that would easily obliterate lesser compounds. It is a molecule born of the fire, perfectly engineered to endure the absolute maximum fury of the stellar furnace. As the methane disappeared from the planet's sky, the unblinking eye of the James Webb Telescope recorded an instantaneous, vertical spike in the signature of carbon monoxide. The spectrum flipped completely, replacing the cold, soft markers of winter with the sharp, rigid indicators of an ultra-hot chemical inferno. This spectacular molecular inversion is what scientists call a perfectly balanced chemical seesaw. As one side of the scale falls into ruin, the other side rises to dominance with absolute mathematical precision. It is a vivid demonstration of how quickly an entire world can rewrite its internal chemistry when provoked by the extreme forces of gravity and heat. through the magic of time-resolved spectroscopy. Humanity did not just deduce this change after the fact. We watched the scales tilt in real time. We witnessed the precise hours where the old bonds broke and the new ones were forged, mapping the fluid boundary where winter gave way to an absolute chemical hell. We have already watched the grand molecular seesaw of the cosmos, the violent destruction of methane, and the sudden, triumphant rise of carbon monoxide as the planet HD 80606b plunges into the solar furnace. But the golden eye of the James Webb Space Telescope was not finished revealing the secrets of this scorched giant. As the raw data from its spectrographs was carefully untangled by astronomers, a new, unexpected signature emerged from the infrared dark. It was a faint, distinct, and deeply profound chemical marker, the unmistakable fingerprint of carbon dioxide. To understand the significance of this discovery, we must look at how this ghostly signature presents itself to our instruments through the delicate art of transmission spectroscopy. The telescope isolates the thin rim of starlight, filtering through the planet's upper atmosphere. As that light passes through the gaseous shroud, different molecules absorb very specific colors or wavelengths of infrared light. Carbon dioxide possesses a famous, unyielding preference for a specific pocket of the infrared spectrum, leaving a sharp, dramatic dip in the data at exactly 4.3 microns. For astronomers, catching this 4.3 micron dip is the equivalent of finding a pristine, unique bootprint in the mud of a deserted mountain trail. It is a definitive, unassailable proof of presence. Before the launch of this $10 billion golden spacecraft, finding carbon dioxide in the atmosphere of a giant planet outside our solar system was an elusive dream. Yet here, wrapped within the turbulent, fire-blasted air of a world 4 times more massive than Jupiter, the fingerprint was carved with stunning clarity into the cosmic ledger. It serves as a majestic chemical tracer, a cosmic baseline that allows humanity to calculate the precise ratio of heavy elements, specifically carbon and oxygen, hidden deep within the planet's ancient core. The discovery of this carbon dioxide fingerprint did more than just add another name to the atmospheric checklist. It forced humanity to confront a radical, fluid state of nature known as disequilibrium chemistry. To appreciate this profound concept, we must first look at the traditional ideal that governed astronomy for generations, the concept of chemical equilibrium. Imagine a quiet, forgotten farm pond in the dead of winter. The wind has died down. The ice has formed a smooth pane across the surface, and all the mud and silt have settled perfectly to the bottom. Everything is at rest. If you know the temperature of the water and the depth of the pond, you can calculate exactly where every grain of sand will sit. For decades, scientists assumed that planetary atmospheres operated like this quiet pond. They believed that given enough time, the chemical compounds in a planet's sky would settle into a peaceful, predictable balance, governed strictly by the local temperature. But the wild, comet-like orbit of HD 80606b shatters this peaceful picture entirely. The planet does not reside in a quiet neighborhood. It travels along a stretched, hyper-eccentric path that takes 111 days to complete. As it executes its rapid hairpin turn around its parent star, the environment changes too quickly for the universe to remain balanced. The temperature surges by 600 degrees Celsius, a terrifying leap of 1,100 degrees Fahrenheit in a window of less than 6 hours. This sudden, explosive injection of thermal energy throws the entire atmosphere into a state of chemical chaos. The molecules find themselves caught in a violent temporal lag. The thermometer is rising faster than the chemical reactions can keep pace. This is the very essence of disequilibrium chemistry, a state of nature where the true composition of the air completely defies the local temperature, because the environment is changing too fast for the atoms to settle into their traditional, peaceful arrangements. To visualize how this disequilibrium plays out across the face of the giant planet, think back to the classic, high-performance V8 engines of our youth. Imagine a finely tuned carburetor running at a steady, quiet idle. If you suddenly stomp your foot flat to the floorboards, a massive rush of raw fuel and air tumbles violently into the cylinders. For a brief, chaotic moment, the mixture is completely unbalanced. The fuel cannot vaporize fast enough. The spark cannot catch it cleanly. And the exhaust fills with a rich, complex mixture of half-burned compounds. The engine is operating in a state of violent disequilibrium, responding to a sudden surge of power before it can find its rhythm. On a global planetary scale, the atmosphere of our roasted giant behaves exactly like that flooded engine. As the star's intense radiation cooks the outer layers of the planet, it triggers massive, global winds that scream across the landscape at speeds exceeding 5 kilometers per second. These supersonic gases do not just travel horizontally. They dive deep into the interior of the world, creating powerful vertical currents, deep vertical mixing. The intense heat roars through the cloud decks, dredging up heavy, hot gases from the deep, hidden reservoirs of the planet's belly. Atmospheric upwelling. These hot compounds are violently thrust upward into the cooler, higher layers of the sky in a matter of hours. Chemical freezing. Once these gases reach the upper atmosphere, they are hit by the sudden chill of space before they have time to chemically adjust to the lower temperatures, leaving them frozen in a state of perpetual mismatch. This violent churning creates a beautiful, chaotic soup, where carbon dioxide, carbon monoxide, and the broken remnants of methane all exist simultaneously in the same space. Under the old rules of chemical equilibrium, these molecules should never be seen together in these proportions. The presence of one should naturally cancel out the other. But in the grand theater of disequilibrium, the old rules are cheerfully discarded. The atmosphere becomes a living, breathing testament to transience, a place where the sky is permanently running to catch up with a sun that refuses to stand still. We have already explored the massive thermal spike and the elegant chemical dance that breaks apart molecules in the flash fry of the solar hearth. But the true physical manifestation of this extreme environment is not merely a quiet change in a lab report. It is a display of raw atmospheric violence on a scale that defies human imagination. As the giant planet rounds its closest approach, the sheer energy of the star triggers a supersonic shockwave superstorm and the instantaneous evaporation of clouds made of solid rock, completely reshaping the face of the world in a matter of hours. To understand the birth of this planetary tempest, we must visualize the stark, terrifying contrast between the two halves of this gas giant. Because the planet moves on such a stretched, elongated orbit, it spends most of its year chilling in the outer dark, keeping its atmospheric layers relatively uniform. But as it plummets toward its parent sun, executing that sharp hairpin turn, one side of the planet is suddenly shoved directly into the path of a solar furnace, 10,000 times more intense than anything felt on our familiar Earth. The day side of the planet absorbs this blistering radiation instantly, its temperature screaming upward by 600 degrees Celsius in a single afternoon. Meanwhile, the night side of the planet, turned squarely away from the fire into the deep dark of space, remains trapped in a state of relative cold. This creates a monumental, unnatural pressure wall between the blazing noon and the freezing midnight, a cosmic gradient so steep that the atmosphere simply cannot maintain its balance. This extreme pressure imbalance acts like a sudden global trigger. The air does not move in a gentle rolling breeze like an August wind across a prairie. Instead, it snaps forward in a phenomenon known to fluid dynamics as a hydrodynamic shockwave. We can think of this simply as an explosive, supersonic wall of moving gas, a global sonic boom that tears through the planet's atmosphere with absolute fury. Imagine standing on a quiet desert plain when a squadron of high-performance fighter jets screams past at low altitude, breaking the sound barrier right above your head. The air itself seems to crack, hitting your chest with a physical, concussive force that rattles the bones. On this roasted giant, that shockwave is not produced by a passing metal machine. It is the sky itself, exploding forward. The supersonic wall rushes from the blistered day side toward the dark night side, traveling at speeds exceeding 5 kilometers per second. To put that into perspective, for an earthly traveler, that is a staggering 11,000 miles per hour, more than 15 times faster than the speed of sound, and a velocity that would circle our entire earthly globe in just over 2 hours. This is not a storm that builds slowly over a damp weekend. It is an instantaneous, roaring engine of kinetic energy that flattens every atmospheric structure in its path, churning the deep Jovian gases into a chaotic cauldron of high-velocity winds. As this supersonic shockwave tears across the landscape, it encounters the planet's primary line of defense, its vast decks of mineral clouds. When the planet is resting in the cold outer darkness of its long winter, the upper atmosphere is cool enough to allow heavy elements to condense. On Earth, our clouds are made of gentle water vapor that drops refreshing rain onto our fields. But on a giant world 4 times more massive than Jupiter, the chemistry is far more industrial. Out in the cold dark, the clouds are composed of silicates and exotic minerals, essentially fine, airborne dust made of liquid rock, iron molecules, and grit. These thick metallic clouds act as a magnificent reflective armor, a planetary shield that bounces a massive fraction of the incoming starlight back out into the void of space, keeping the lower layers of the world insulated. But as the supersonic shockwave hits and the temperature crosses the threshold of 1,100 degrees Celsius, the armor fails completely. The intense thermal energy does not cause these rock clouds to produce a heavy mineral rain. Instead, it triggers an instantaneous global flash evaporation. Think of an industrial steel foundry, where a massive iron crucible is tipped, pouring molten metal into a furnace. If a drop of water hits that white-hot liquid iron, it does not simmer. It flashes into steam in the blink of an eye. On a planetary scale, the star's raw fire treats the rock clouds with the same absolute power. The silicates and iron dust are instantly vaporized, turning from thick, reflective clouds into a completely transparent, superheated gas. In a window of less than 6 hours, the planet's armor is utterly dissolved, stripped away like a layer of wax melted off a hot engine block. With the clouds gone, the sky clears into a terrifying, transparent void, allowing the unmitigated, raw fury of the solar furnace to penetrate deep into the lower belly of the planet, cooking the world from the outside in. When we lift our eyes from the brief, chaotic window of a single afternoon and look toward the multi-billion-year horizon of this system, we encounter a process of majestic, slow-motion engineering. This evolutionary journey is known to astrophysics as tidal circularization. We can think of this simply as the long, patient taming of a cosmic maverick, an unyielding process where the wild, stretched-out rubber band of an orbit is slowly reined in by the invisible hands of gravity, reshaping a chaotic wanderer into a perfectly disciplined sphere. To understand how this cosmic reshaping occurs, we must look closely at the heavy iron brake shoes of tidal friction that clamp down on the planet every time it ventures into the solar furnace. As the planet, HD 80606b, completes its headlong plunge, the intense gravitational tug-of-war distorts its massive body into an elongated egg shape. This mechanical squeezing generates an unimaginable amount of internal heat deep within its core. In the strict, unbroken bookkeeping of the cosmos, that thermal energy cannot be created from nothing. It must be paid for using the planet's own kinetic energy, its raw, forward speed. Every single time the giant executes its hairpin turn around the star. The internal friction steals a tiny fraction of its momentum. The planet leaves the presence of its sun with just a whisper less steam than it possessed when it arrived. To visualize what this loss of momentum does to the path of the world over eons of time, think back to the classic grandfather clocks of our youth, watching the heavy brass pendulum swing in a magnificent, wide arc. Imagine that every single time that heavy pendulum reaches the absolute lowest point of its swing, it brushes gently against a tiny piece of soft velvet. The velvet does not stop the pendulum entirely, it merely robs it of a microscopic fraction of its energy. The next time the pendulum swings back up, it cannot climb quite as high into the air as it did before. The highest point of its journey drops lower and lower with every single tick of the clock, while the lowest point, the place where it brushes the velvet, remains exactly the same over thousands of swings. The wide, dramatic arc is systematically ground down until the pendulum moves in a tight, quiet, and perfectly restrained path. On a planetary scale, this is precisely how tidal circularization carves its masterpiece out of chaos. The point of closest approach, the solar hearth, remains fixed like an unyielding iron anchor, dictated by the proximity to the star's immense mass. But the farthest point of the planet's journey, where it slumbers in the freezing darkness of the outer porch, is steadily and relentlessly brought down every 111 days as the planet completes another agonizing lap. The far end of its long, skinny loop is reined closer to the center. The extreme comet-like oval is being squashed from the outside in, rounding out the edges with a patient geometry that takes millions of years to complete a single inch of progress. As this slow-motion collapse plays out across the deep dark of the universe, the planet is guided toward a highly predictable, civilized destiny. Astronomers have mapped this long-term retirement plan, charting a path that will eventually transform this wild outlier into a standard, orderly member of the celestial community through a series of distinct evolutionary stages. The shrinking year, the long cold winter of the planet's year, is gradually eliminated as the outer boundary of its racetrack shrinks by thousands of miles with every passing century. The permanent bake, as the orbit rounds out, the dramatic flash-frying events dissolve into a steady, unchanging climate, baking the world into a perpetual, uniform inferno, the final lock. Eventually, the perfect circular path forces the planet into a state of tidal synchronization, a permanent orientation where one side forever faces the blinding glare of the sun, and the other remains trapped in eternal night. When we look at HD 80,606b today through the magnificent golden mirror of the James Webb Space Telescope, we are catching a rare glimpse of a world caught mid-stride in this beautiful transition. It is a living laboratory of deep-time physics, a bridge between the untamed, eccentric rebels of the early universe and the quiet, settled systems we know so well. It reminds us that no matter how violent or lopsided a journey may begin, the universe possesses an underlying, unyielding desire for balance, symmetry, and ultimate order. Now, as we approach the final chapter of this planetary epic, we witness the ultimate destiny prepared by the laws of nature, a state of absolute, unyielding stillness, known to science as tidal locking. We can think of this simply as the final setting of the cosmic emergency brake, a permanent alignment where the planet is forced to forever turn a single, unchanging face toward the blistering glare of its master star. To understand the profound mechanics of this final rest, we must look at the relationship between a planet's spin and its journey through space. In the early days of its life, our gas giant was a wild, spinning top, rotating rapidly on its axis while hurtling along its elongated racetrack. But every time it squeezed through that tight, close-up hairpin turn, the star's immense gravity acted like an invisible hand, grabbing the planet's bloated, egg-shaped body. This continuous, rhythmic pulling created a permanent drag on the planet's rotation, slowly and methodically unscrewing its internal clockwork. Think of a massive, heavy iron flywheel spinning at thousands of revolutions per minute inside an old steam engine plant. If you were to apply a steady, peaky, unyielding pressure to the outer rim of that wheel day after day, year after year, the furious spinning would eventually lose its steam, slowing down to a perfectly controlled, predictable crawl. Through the patient application of this gravitational drag, the universe eventually achieves a state of perfect, synchronized harmony. Tidal locking dictates that the time it takes for the planet to complete one full spin on its own axis becomes exactly equal to the time it takes to complete one full journey around the star. To visualize this perfect synchronization, imagine taking a classic vintage sports car out onto a perfectly circular test track, the unlocked drive. If you drive around the track while spinning the car in continuous circles, your headlights will flash across the infield, the outer grandstands, and the dark woods beyond the locked drive. But if you adjust your steering so that the driver's side window is permanently locked onto the central mechanics tower in the middle of the field, you will complete one full rotation of the car in the exact same time it takes to complete one lap around the track. For HD 80,606b, This means the chaotic days of shifting winds and exploding shockwaves will draw to a permanent close. The planet will no longer experience the frantic 6-hour flash-frying events of its youth. The cosmic flywheel will lock into place with a quiet, definitive click, anchoring the world in a permanent, unbreakable embrace with its sun. The consequences of this final locking rewrite the very nature of the planet's geography, splitting the giant world into two completely independent, eternal kingdoms. The side of the planet turned toward the star becomes a permanent, unblinking eye of fire, an absolute day side where the midday sun never sets, hanging suspended at the exact same spot in the sky for trillions of years. Here, the atmosphere is baked into a uniform, unchanging inferno, a landscape of perpetual solar bombardment where the rocks themselves remain forever vaporized. Meanwhile, the opposite side of the world is turned permanently away, facing the cold, empty void of deep space. This is the eternal night side, a kingdom of absolute darkness and freezing silence that will never see a single ray of sunrise. In this dark hemisphere, the atmospheric gases cool down into a permanent, heavy freeze, creating a vast, dark porch of quiet shadows that stands as a stark contrast to the roaring furnace just over the horizon. Between these two extreme worlds lies a thin, circular ribbon of land known as the Terminator Line. We can think of this simply as the eternal twilight zone, a narrow frontier where the blazing sun permanently rests right on the edge of the horizon, casting long, dramatic shadows across the landscape. It is a place of permanent dusk, a quiet, stationary boundary where the absolute fury of the day meets the absolute peace of the night. As we let our minds rest upon this final, locked destiny, feel the deep, reassuring sense of comfort that comes from the ultimate order of the cosmos. The universe does not allow chaos to reign forever, no matter how wild, eccentric, or violent a planet's journey may begin. The patient, unyielding laws of gravity are always working to bring that world home to a state of absolute balance and permanent rest. The long, frantic loops are rounded out, the furious spinning is calmed, and the machinery of the heavens settles into a quiet, harmonious standstill. When we turn our gaze back from this wild, chaotic frontier and look upon our own familiar neighborhood, a profound, humbling realization washes over us. The true lesson of HD 80606b is not found in its distant violence, but in the magnificent, rare tranquility of our own home. Our solar system is not the boring rule of the cosmos. It is a beautifully insulated sanctuary, a masterwork of absolute planetary peace. Think of the majestic worlds that share our local sky: Venus, Mars, ringed Saturn, and our own precious blue Earth. Unlike the hyper-eccentric maverick we explored tonight, our planets travel along calm, dignified, and nearly perfect circular tracks. Their orbital eccentricity is so microscopic that they maintain a steady, unchanging distance from our life-giving sun. Year after year, century after century, we do not experience global seasons that flash-fry our oceans in a single afternoon, nor do we endure supersonic shockwaves that tear our skies apart at 11,000 miles per hour. Our atmosphere remains a stable, gentle blanket, allowing the delicate chemistry of life to grow, adapt, and flourish in a state of permanent security. This profound peace is not a random accident of fate. It is the product of an incredibly elegant gravitational architecture. In our system, giant Jupiter does not act as an eccentric bully or a reckless disruptor pushing smaller worlds into a solar forge. Instead, it sits quietly in the middle distance, utilizing its immense mass to serve as a grand cosmic shield. A big brother that sweeps away dangerous debris, stabilizes the tracks of the inner planets, and keeps our orbital sandbox perfectly safe. Our Sun is a solitary, remarkably stable furnace, free from the destabilizing long-distance nudges of a twin sister star. This structural harmony creates a pristine oasis, allowing our Earth to sit squarely within a golden paradise where water remains fluid, the air remains sweet, and the deep rhythms of nature turn with the comforting predictability of a well-crafted grandfather clock. Looking out at the fiery, tortured playgrounds of the deep universe does not make our world feel small. It makes our home feel infinitely precious. It transforms the night sky from a cold, terrifying void into a grand blanket of gratitude. As you let your mind rest upon this beautiful contrast, feel a deep, settling wave of comfort wash over your thoughts. We are the fortunate residents of a quiet harbor in the middle of a wild and turbulent cosmic ocean. The supersonic tempests and molecular explosions of the deep dark cannot touch you here. You are safe, insulated, and completely protected within the gentle, orderly clockwork of our home system. The great golden eye of the telescope continues its silent vigil a million miles away, mapping the wild edges of creation, while our own quiet Earth rolls smoothly on its ancient golden tracks. The day's work is entirely finished. The gears of the universe are running flawlessly, and the night is perfectly secure. Let your eyelids grow heavy now, trusting in the steady, beautiful harmony of the stars. Sleep deeply, comfortably, and peacefully as you drift gently away into an undisturbed and magnificent rest.